All right, so it's a pleasure to introduce Bill Casselman, whom I've known for a long, long time. He was an undergraduate here at Harvard, received his PhD at Princeton, and then spent most of his professional life at the University of British Columbia. The title of his lecture is The Origins of the Langlands Conjectures. So it's your turn.
Thank you. What Wilfried might have mentioned was that he and I and Langlands and Shimura and Vey and a whole bunch of people in this story were all in Princeton in the same year a very long time ago.
That's right.
So anyway, what I'm going to talk about is, I've given many talks on the origins of Langlands conjectures, none of them entirely successful. This time I thought I would trace a simple problem all the way through to see what Langlands conjectures might say about it. You can see, I think, presume you can load this file of slides from Harvard, but also from UBC. Langlands has made many contributions, but it's the discovery of the L group, or what we now call the L group in a sense that is the principal feature. And I'm going to try to explain that, as I say, by tracing origins of a simple problem. There's a sobering thought I had as I was preparing this. More time separates us from Langlands conjectures than Langlands conjectures from Ramanujan's. And Ramanujan's conjecture is, in a way, the beginning of the story. Here's an outline of what I have to say. I'm going to talk about a classical problem in number theory. Let R of L of n be the number of ways in which you can express a positive integer n as a sum of L integral squares. So, for example, R2 of 4 is equal to 4, because you can write it the way it looks. So this was a very, I won't say a very commonly worked on problem in the 19th century, but some very famous people did that. When k is small, they found explicit formulas. Gauss famously found one for R3 when he was very, very young. And later on in the century, Smith and Minkowski found one for 5, the sum of 5 squares. But the point is, in a way, that odd L, when L is small, when odd L behave very, very differently from even L, and I'll assume that L is even from now on. In that case, the first major, well, to give you an idea of the flavor of the problem, look at some pictures. It's kind of a random quality to it. It depends, it seems to depend, or it does depend in a erratic way on what n is. As you can see from the graph, it looks like a bouncing ball of some kind behaving very erratically indeed. And the reason for that is because the R2 of n, just R2 of n alone, the simplest one, depends on the factorization for n. Fermat already knew that if I had a prime p, then it can be expressed as a sum of squares if and only if that prime is congruent to 1 modulo 4. Jacobi generalized this. As far as I know, he was the first one to do so explicitly, although Gauss must have known the answer. It's equal to, R2 of n is equal to 4 times the sum of the divisors congruent to 1 modulo 4, and the difference of that with the number of divisors congruent to 3 modulo 4. And he also got a formula for R4 of n, which again might have been known earlier. It's A times the sum of the divisors of n. Jacobi went on to discover formulas for R6 and R8, but he stopped at that point at some time. And it took quite a long time for him to find it. One of the basic tools, and we'll see this later on in Jacobi's work, and in all subsequent investigations, is a theta series, which I take the sum q to the power n squared. And you can rewrite that to be a sum over all positive integers. And because if I take the nth power of theta, then it's equal to a sum whose coefficients are the number we're looking for, are L of n. For example, you can see theta squared there. So the problem was reformulated by Jacobi how to find a formula for theta to the nth power. One hint as to what will happen later on is the fact that theta of L, and I'm pretty sure Jacobi knew this, that theta of L can be defined as a function which is holomorphic on the entire upper half plane by setting q equal to e to the 2 pi I z. And if I do that, then I get a series that I explain in the formula here. And R of L of n is bounded by a polynomial, and this term is exponentially decreasing if y is positive. So this is definitely an analytic function as long as y is positive. Now, there were all kinds of as I say, randomly people seem to work on this, and it was very hard to track down. It still is quite hard to track down all possible contributions. But there was a summary of some kind given in a paper by a relatively obscure English mathematician named J.W.L. Glashier, a very eccentric fellow. In fact, he was not only a mathematician, he was specialized in numerical computation. And he was most famous actually as an astronomer, and was at one point offered the job of the Astronomer Royal to succeed John Bedell at George Bedell area. Anyway, he, eccentric though he was, he worked very hard on the problem of sums of n squared. And he published a paper with a table which I reproduce here. So you can see it's a rather messy table. He has all these functions. So the way I've done it, I've taken his table and I've color annotated it so that the terms in blue are divisor sums, just like the one in Jacobi's formula. So R2, R4, R6, R8, those are all entirely divisor sums. But for R10 already, you get a divisor sum, the blue part, and then you get an extra little part, chi4 of n. I'll say something more about chi4 later on. And then that continues on. From 10 on, you get all these supplementary terms, which are, well, we'll see. We'll say something about them. And so the divisor sums are very easy to calculate. And then you have these extra terms, which are pretty much mysterious to people at the time. What's true is that the divisor sum terms clearly dominate what's going on. The terms in red are asymptotically as n grows much, much, much smaller than the terms in blue. So, but at any rate, in every case, you get that RL of n for L even is equal to some kind of divisor sum and then plus some supplementary term. Glashier here has normalized the supplementary terms so that each one of them, first of all, they all have constant terms 0. And so they begin with Q itself. And then he's normalized things so that that coefficient of Q in each one of the supplementary terms is 1. And well, it's a curious table. But in a way, a great deal of mathematics is hiding in this table, as we'll see. For example, if you look at L equals 12, which was the first really complicated case, it looks like this. There's no rhyme or rhythm to the way the numbers appear. But Glashier did notice that it has a multiplicative property. If m and n are relatively prime, then the is equal to the product of the coefficients for m and the product and the coefficient for n. And what we would now do, and in fact was done a little bit later by somebody else, we write this as a Dirichlet series. We write sigma of omega n over n to the s, and that's equal to an Euler product of some kind. We don't know yet what the term for each p is, but we can write it as a product for p series. It looks something like that. Are there any questions? No. So I plotted it. So here we have a plot. It's a log-log plot. So I've taken log p and log of whatever coefficient I'm involved in. The black terms are the divisor sums, and the red terms are what me and Glashier call the supplementary series, what G.H. Hardy also calls the supplementary series. So these both grow geometrically, but the supplementary series grows much, much more slowly than the other term. In fact, about half as fast, in fact. And pretty much the terms for sigma p are, in fact, the interesting ones because of the multiplicative property. So I've reproduced the table again, just to bring to what questions might occur to you. So the first question is, well, can we extend the table? Can we look at R20, R22, R24, and so on? What are the chances of actually finding formulas in those cases? The second question is, why are the divisor sums so complicated? Well, we'll say something about that. And why sometimes no? What do the supplementary series come from? In the words of Isidore Rabi, who asked for those? And what do they mean? Where do they come from? Can we estimate them? Is there any clear way of estimating it? And the next question is, did the multiplicative property always hold? Is there some fundamental reason why that's the case? And another question from the Dirichlet series, the Euler product I wrote down, is we wonder if we can actually say something about the P series itself. The final question I ask is, what about other quadratic forms? What's special about sums of squares? Well, suppose we look at any integral positive definite form. So in general, can we just bring some organization into the chaotic business? The situation just seems kind of confusing to us, and that's unsatisfactory. We expect somehow a little organization to appear. But it's intriguing. Things don't look hopeless, but they don't look very optimistic either. Glashier wasn't very happy about what was going on. He worked, I have to emphasize, Glashier had to work very, very hard to get those formulas. It's to anybody actually setting out to find formulas for RL, where L is up to 18, it's an enormous amount of work, and I think only somebody like Glashier, who really was very happy doing computation of a ridiculous level, would have done it. And it is rather amazing that he actually discovered all those formulas. But his comment was, he was unhappy. He really was unhappy, and he said, the only complete and effective method of research in such investigations is afforded by the processes of the theory of numbers. Any method dependent upon elliptic functions, which is what theta to the L is necessarily partial and inadequate. So he really, he just felt you should do more elementary, that the whole process should be more elementary somehow. And the elliptic functions were just a crutch, which eventually one could throw away. However, what's true is that in the course of the 20th century, it became clear that the opposite is true, that, that somehow elliptic functions, or modular forms as they appeared to Glashier, it's an inevitable component of number theory, and something we can't do without. It's unfortunate or fortunate, it's the way things are. So Glashier somehow, the problem itself is so simple that he felt it should have a simple solution, but we're, I think, more adjusted to the fact that simple problems can have insanely complicated solutions. And that seems to be what we're staring at here. About 10 years after Glashier's paper, and I'm not aware that there was any literature in between those 10 years, about 10 years, Ramanujan read Glashier's note. Probably Hardy suggested it to him. I can't find an explicit reference in Hardy's writing, but that's what one suspects. And Ramanujan found formulas for R20, 22, and 24. I won't write them down because the way Ramanujan wrote them was more complicated than the way Glashier did. It's not the same notation, except for 24. And the 24, he has a formula just like Glashier's. Here are the divisor sums over here. This means the sum of 11th powers of divisors. N over 2 is taken to be 0 if n is not even number. And you get this in that case. And the supplementary terms, it looks like one of Glashier's terms, but it's got a function tau in it. And tau is very famous, I think invented by Dedekind. It actually occurs in a very simple way in a product of Q polynomials. So, and this is well known. It occurs in the elliptic, in the theory of elliptic functions, because it represents the points of the upper half plane represent elliptic curves. And the function delta here, this product, when I set Q equal to E2 pi I n z, delta represents the discriminant of the elliptic curve. In particular, it doesn't vanish anywhere on the upper half plane. So, yeah, so that plays an important role later on. And then following Glashier, Ramanujan noticed or conjectured, he's a little bit vague about that, that the multiplicative property holds as well here. I want to say that Glashier was really the one who discovered the multiplicative property, and Ramanujan made it famous. Unlike Glashier, however, Ramanujan actually looked at the P-series itself, and he found empirically something that Glashier might have noticed. It's sort of puzzling to me that Glashier, in fact, hadn't noticed it, because it really sticks out in his examples. The P-series satisfy a difference equation of order 2. And when you combine that, you get a formula for the P-series itself as a rational function, which you can write on the right-hand side. So in Ramanujan's case, he can write the Dirichlet series of tau n over n to the s as a product of 1 over something. And that's what we have here. It's an amazing formula because, in fact, the notation of Ramanujan is exactly the notation we use now. I don't think that Glashier ever wrote down the Dirichlet series like this. This is Ramanujan's invention. It's rather striking, in fact. Ramanujan also did something else. He really was a talented guy. He found the simple expression for the divisor sum when L was congruent to 4 modulo 8. Therefore, he answered part of the questions. In other words, he found a reasonably simple expression for the divisor sum in certain cases. I'm not sure why he couldn't deal with the arbitrary case congruent to 0 modulo 4, which is actually easier and discovered later by Hecke. But even more interesting, what Ramanujan did was he took the characters, well, he took a polynomial related to the denominator in the formula, and he factored it as a product of well, just by finding the roots. And of course, the p11th occurs here, so we can factor it like this, where alpha and beta, where their product is equal to 1. Offhand, that's all we know about it. But of course, it's very natural to guess at this point. You're looking at this formula and you're wondering if it makes any sense. It's very natural to guess that, in fact, the roots were complex conjugates. And in that case, I can write one of the roots as 2e to the 2 pi I theta for some theta in 0, 2 pi. And equivalently, we have cos theta is equal to tau pi over the power here, 2 times p to the 11 halves. And this is actually strongly, I don't know that either Ramanujan or Glashier ever computed the graph or drew the graph that I illustrated earlier, but it's certainly very strongly suggested by the graph, which suggests, in fact, a good deal more. It's not clear to me how much excitement anybody felt about this guess. It's just not clear at all. However, Hardy paid a lot of attention to it. And I think the reason was, so Glashier's results were very striking to somebody who had seen them, but somehow they didn't really resonate. Ramanujan's paper resonated a great deal more because a lot of English mathematicians were interested in elliptic functions. And the function delta was really a very famous function, with a lot of people working on it for various reasons. Hardy wrote a book later based on some lectures in England in the mid-30s, a very famous book on Ramanujan, which you can find online, I think. He wrote a very famous quote: "We may seem to be straying into one of the backwaters of mathematics, but the genesis of tau n as a coefficient in so fundamental a function compels us to deal it with respect." In some lecture recently, Sarnak says that Hardy was being ironic. There's no evidence whatsoever that that's the case. I think Hardy really just was very puzzled mostly. He just didn't know quite how to deal with Ramanujan's conjectures. I think it's just not clear what people thought about it. Hardy hadn't given up the mathematics of these things completely because he had a student in Robert Rankin who was still producing interesting results related to Ramanujan's conjecture. But that doesn't violate my statement because Rankin was a Scot. Meantime, however, the Germans had been taking off working on such subjects, and they were doing actually pretty well in it. There's if you read the literature of the English at this time, there seems to be some English nationalism involved. They don't refer to the Germans, Hecke and his students particularly, they don't refer to them as often as they should. There's some strange psychology going on. One thing that Ramanujan might have done, but did not, was examine the statistical distribution of the angles in this formula. So I made a bar graph. It's actually not easy to do this, but it's not too hard either. A bar graph of distribution. I took 2,500 values of Glashier's function omega, the same one I drew graphs for earlier. And that was for R12, and I made the graph here, and you get the distribution of the angle between 0 and pi like that. It's a very nice distribution, and it's actually, as we'll see later, there's a now proven formula for that distribution. There's no trace, I see no sign in any of the classical literature that people had actually done that distribution, actually thought about it. However, I have to say that the distribution for R12 contrasts with the distribution for R10. And here, the supplementary term in there, as I said, it has a simple formula. Chi-fourth was a supplementary term. Chi-fourth of P is chi-fourth of N actually, it doesn't have to be a prime. It's a very simple formula. It's the sum of fourth powers of the numbers basically which divide P in the Gaussian integers, Z join the square root of I. It vanishes if P is congruent to 4 modulo 3, as we've seen from Fermat's result, and it's uniformly distributed for other values of 1, as follows from a difficult theorem of Dirichlet. I see no mention of this. It's rather puzzling. But around 1965, as I'll mention later on, it became a very famous question. Okay, so we have, at this moment, we have a number of questions. So we have to know, we have Ramanujan's conjecture about the multiplicative property. We have Ramanujan's conjecture about the difference equation. We have his Ramanujan's question about the size of the coefficients in the tau, and we have the question of the distribution. That's 4 different questions involved. That's pretty good, actually. So the answers, a lot of the answers are supplied by Erich Hecke. Erich Hecke took up the subject. However, excuse me, I forgot. The most important thing was about a year after Ramanujan's first 2 conjectures, they were actually proven, the multiplicative property and the difference equation were proved by a British mathematician who had actually been born in America named Louis Joel Mordell. As I said, if we set q equal to 2 pi I z, we get a modular form for delta related to elliptic functions, which is actually invariant or equivariant or covariant. I'm not quite how to say it. Anyway, it's relatively invariant under SL2Z. Mordell defined operators, which are now called Hecke operators, on such forms. Sarnak, again, in a recent lecture, suggests that the question is, where did Mordell get the idea of defining these? And it's an interesting question. I hadn't thought much about it. Sarnak suggests that maybe he learned from a paper of Hurwitz, which is actually a very famous paper at that time. And that's possible. That requires a little more reading, actually. Hurwitz wrote a very famous essay on modular forms. Anyway, Mordell defined these, and then it's easy to see from the definition of these operators that they satisfy the multiplicative property. And then Ramanujan's conjecture about multiplicativeness, you have to show that it's an eigenfunction with respect to these operators. And he proved this by using well-known properties of delta. For example, the fact that delta has no zeros, so you can divide by it and you still have a reasonable function. He just has to show that Tn of delta is actually bounded on the upper half plane. And that shows that it's a constant. And that's what he did. Nowadays, this step is rather elementary because we know a good deal about what those functions like delta satisfy. And particularly, we know that delta is unique in this situation, up to constant. So, and Tn of delta is also a basic properties which make it automatically a constant times delta. One curious fact about Mordell's proof is I think he refers to squares, but only as an aside. He doesn't really use any relationship with sums of squares, but just uses well-known properties of delta. It's very specifically oriented to that. I'm going to have to tell you, I think, in order to understand what Langlands did even, I have to explain what the operator T of n is. And I have to tell you what a modular form is. So the notion of modular form, I'm not quite sure who first noted, but it already occurs in Eisenstein. It's rather, in fact, Eisenstein defines it in a very nice way, which is very simple. It's a function on lattices in the complex numbers. So lattice is a copy of Z2, and it's specified by a basis for the lattice. And we can orient things so that the ratio of the first basis element over the second is positive. And 2 such pairs give rise to the same lattice when one of them is transformed to the other by a matrix in SL2Z. So basically what we're saying is that basis elements modulo SL2Z are just, it's a space of lattices, or elliptic curves, which is where the modular forms come in. And a modular form is a function on lattice, well, some mild growth condition, which I won't specify, and 2 other conditions, which is when I look at when I scale the lattice, the function scales by a negative power of lambda. And when I apply my gamma in SL2Z, then, or well, most often in this lecture, SL2Z, then it's just invariant. So as I say, this definition seems to be basically due to Eisenstein, although a little vaguely, but it's certainly by the time of Hurwitz, it was a well-known definition. So a modular form is a function on the set of lattices, which scales nicely. And if I restrict to point Z1 as my basis, then I get a function on the upper half plane, and this transforms in a slightly odd way under fractional linear transformations, which I won't specify yet. So for example, if I use the property that my function is invariant under matrices, upper unipotent matrices, then it's periodic with respect to the integers, horizontal translations. And that means that I can write it down as a series. And the growth condition then becomes very simple. It just means that C of n is equal to 0 for negative n. It was well known that the power, the theta, the function we're interested in, the power of theta to the 2k, is a modular form of weight k for some gamma of finite index, not gamma equals SL2Z, but something of finite index, which is well known actually. This is where we need the L to be even, because if I take a power of an odd power of theta, it behaves much more oddly. Much more oddly actually, but also more interesting in a way. So now I want to define, and this is Hecke operators. So we have a function of lattices, and we want to define an operator, T of n, which takes one function of lattices to another function of lattices. Well, that's very simple. If I have one lattice contained in another, then I can apply the principal divisor theorem, and I get a pair of the sublattice is specified by a pair of integers, n1 and n2, where n2 divides n1. So if I have a function which is invariant under, well, a function of lattices, then I can define another function of lattices by a pair n1, n2 by taking the sum over all the sublattices of a certain index. And for example, if I take a prime pair P1, then I get a sum of P plus 1 lattices, the P plus 1 lattices of the proper index type. And then I can define Hecke operators to be the sum over all of those Tn1, n2, where n1, n2 are multiplied to give n. That's what I call the simple Hecke operator. And then there's a normalized Hecke operator where you multiply this by n to the k minus 1. Either way, the multiplicative property is trivial, actually almost trivial to verify because of the Chinese remainder theorem. Okay. What's a little more interesting is the P series, but on geometric grounds, you start fiddling around with this definition of lattices. You can see on the geometric argument that you get equations, which I write down here. I won't state what they are exactly. They're fairly simple equations, and they're a little bit complicated because it depends on whether the n here is equal to 1 or not. But in fact, when you look at the TP of itself, then somehow things get swallowed up a little bit, and you get a very simple formula. And this is equivalent to Ramanujan's difference equation, and hence applies immediately that you get the Euler product he wrote down. This is pretty much what Mordell did. Mordell talked about a lot of other problems related to Ramanujan's paper, but that's the main result of the paper. Mordell's proof leaves unanswered a lot of interesting questions, which I'll raise in a moment, but there's a very simple question I'd like to talk about right now. These operators, T of n, we call them Hecke operators. So the question is, why don't we call them Mordell operators? Well, I don't really know. What I know is that Mordell seems very casual about the whole business. He doesn't seem to really have his heart in the matter. What I suspect is that Hardy had a great deal of influence on his work, and that Mordell was kind of embarrassed, but there's no way of knowing whether that's true or not true. What I do know is that Mordell is kind of careless. So he remarks that Ramanujan made similar conjectures for functions R10 and R16, but that's actually not true. If you go back and look at both Ramanujan and Glashier, they actually talk about other cases as well. So I think Mordell didn't read Glashier or Ramanujan very carefully. My guess is, again, wild guess, that Hardy explained the problem to him and he never actually read either manuscript. But what he does write in his paper is there are other cases where Ramanujan talked about, as we know, he talked about 2022 as well as 24. And what Mordell says is that these results, he says that Ramanujan made similar conjectures for other functions. He didn't get this part right, but he did have other functions. And these results can be proved, he says, by the aid of the principles used in this paper. We should, however, have to consider new invariants of a subgroup of the modular group, so other than SL2Z itself, and it seems hardly worthwhile to go into details. So the last part that seems hardly worthwhile to go into details, I think it kind of doomed him. You're not going to name an operator after the guy if he doesn't even want to own it carefully, I think. So there are indeed some technical problems involved in defining the right Hecke operators for congruence groups, as was involved. Hecke did a really nice job of it. It's not a completely trivial problem, but it's not too difficult either. In a way, these problems, curiously, these problems weren't really understood until the 1960s. And that's because of work of Langlands. So it's a sort of a side product of Langlands' work. I think Mordell just didn't understand he was sitting on top of a gold mine. So he never, as far as I know, I didn't track all his papers, but he doesn't seem to have ever looked at problems like this again. And in some late reminiscences, he's given many talks later in his life reminiscing over his life as a mathematician, wrote even a very small booklet on it. As far as I know, he doesn't refer to this paper again. He became famous for his half of the Mordell-Weil theorem. And that he talks about, but this he does not. A curious question. I'll say more about Mordell at the end of my talk if I have time. So let me summarize what we have at this point if we combine Mordell, Ramanujan, and Hurwitz. So we have a space of modular forms which transform in a certain way with respect to an integer k. And we have the subspace of cusp forms. So the modular forms are allowed to have a constant term in the expansion of the series. The cusp forms have a zero constant term. And in fact, well, it's a little bit vague and not quite clear to me that the classical people knew quite what a cusp form is. We see it now in terms of an inner product, and it's orthogonal to some other space, which is not. Anyway, they have vanishing constant terms. And both spaces have finite dimension. I don't know that this was known explicitly. Certainly a dimension formula is not apparently known at this point, although it could have been. There was no technical problem in it. The difference in dimensions is most 1, since gamma of 1 SL2Z has exactly 1 cusp, and the complement by a function called an Eisenstein series, which was in fact first defined by Eisenstein. So Eisenstein is interested around 1850, I think. He's interested in rewriting the theory of modular forms and elliptic curves. And he anticipated a great many results which are now attributed commonly to Weierstrass. And particularly defined these functions which I write down there. The notation is the standard one in modular forms, but not. So G of k is the sum over lattice points of omega to the k. Eisenstein, curiously enough, there's some reference in the literature of this paper by Eisenstein because he was the first person to actually prove rigorously that this function converged to an analytic function on the upper half plane. At that time, convergence questions were rather vaguely dealt with. Anyway, Eisenstein had some trouble with it, and he spent a great deal of time just talking about convergence, where we would consider it almost trivial. And then he also found, apparently, he's attributed to him, but I haven't found it in his papers. He found a formula in terms of the series for the function when I restrict my lattices to Z1, base is Z1. And I get this formula. So this is a function. It's got some funny terms in it, but it's also got the divisor sum. So this series expansion is in a way the origin of the divisor sums that we've seen in the formulas for our L of n. So of course, what we now know is, and even at that time, I think it was known that the constant term of G of k is that these two terms are somehow related. So when I divide, I get a function. I can divide this by the constant term. I get a function which starts out with 1, and the factors of pi disappear because we know about the value of zeta of 2k. And so we do indeed get a function which is integral, rational coefficients and divisor sums. And all the erraticness which appears in Glashier's formulas is because of the Bernoulli numbers which appear in the constant term of G of k. So as I say, this is attributed to Eisenstein. There's a rather obscure book written by Weil in the mid-60s on this work of Eisenstein. I'll show it in the reference list at the end, but I haven't been able to find it. Anyway, the formula is contained in Hurwitz's Habilitationsschrift, referred to by Mordell and known to Hardy. The point is, as I say, that these are the responsible for the divisor sum. So once you have this formula and its cousins for congruent subgroups, then you can explain all the divisor sums in one part. It's funny that this was not known to Ramanujan and Hardy. Okay, so I'll say more about GL2. Erich Hecke took up the work about 10 years after Ramanujan. He began rather slowly, but in the course he worked all the way through the 30s up into the late 40s after the war. And he changed it completely. Hecke, it's hard to summarize Hecke's thing, except that he just made it he established the foundations of the subject of modular forms, of holomorphic modular forms. And he had a large number of students who worked on problems and also answered basic questions. So basically extended to arbitrary congruent subgroups, the theory that Mordell had begun. And it's hard to underestimate exactly what he'd done. So first of all, he defined Eisenstein series. That was one of his early papers. He said as much as you can say about them, including the series formulas that we need for divisor sums. He defined the operators T of n in a rather nice way, which is still the way we define them now in graduate courses. What's funny, and when I have level 1, then T of pp just takes a lattice to the function evaluated at p times the lattice, which just multiplies it by something, by some scalar. But now, under Hecke's definition, it becomes a little more complicated, and it becomes some twisted action by the diagonal subgroup of gamma 1 quotient gamma n. And then most importantly, his student Hans Petersen defined a Euclidean norm on the cusp forms, and according to which the Tn are self-adjoint. And this is an enormous thing. This means that my space of cusp forms is a direct sum of eigenspaces for the Hecke operators. And we can see that Mordell's property becomes something very general for arbitrary level, because I can have the multiplicative property as long as I'm dealing with eigenfunctions for the Hecke operators. There's a question in my mind as to what, with both Hardy and Ramanujan and Mordell, and with Hecke and Petersen and his students, it's very hard to tell what the advisor actually contributed. But anyway, Hans Petersen, this is one of the few things that Hans Petersen did which became famous. Hans Petersen was a Nazi during the war, and his reputation suffered greatly. Hecke probably knew a formula for the dimension of SK, although I haven't seen it. It depends on Riemann-Roch, which is quoted by both Hurwitz and Hecke. And I'm not sure why Hurwitz hadn't actually proven something like this. He defined L functions in the general way as Ramanujan, but now we have this extra factor, epsilon of P, coming from the slightly different definition of T of PP. So this is a finite character of the, well, a character of the multiplicative finite group of Z mod n. He found a good form of functional equation, not a perfect form, as I probably mentioned later, but a good form, and he showed that the function was entire. Hardy raises the question of the functional equation for Ramanujan's case, and he asserts that Ramanujan must have been, that the functional equation must have been familiar to Ramanujan, but he said, but he could not find his papers. He refers to an obscure paper by an English mathematician named Wilken for a proof of the property of entirety and the functional equation. That may be, Wilken's papers are strangely corrupted on the internet. There's no good copy available publicly. So I can read 1 or 2 pages of his paper, but not all of them. Wilken was interested in any rate in something else, and he certainly doesn't emphasize that he had found a functional equation for this. It doesn't seem to have been of importance to the English mathematicians. It's very hard to read their minds from this distance. Because of Petersen's results largely, he knew fair estimates on the magnitudes, and probably conjectured that you had a Ramanujan estimate of the same kind here, although again, I don't see it explicitly. And he extended earlier results on the sums of squares to other positive definite integral quadratic forms. He worked very, very hard on this, and he has a number of very beautiful papers which are quite readable even now. After the war, there was a more interesting contribution by another student of Hecke's. Hans Maas extended the theory to include eigenfunctions, not holomorphic functions, but eigenfunctions of the non-Euclidean Laplacian on quotients of the upper half plane. This was an extremely interesting idea and led to a fruitful generalization of the notion of modular form, something we can now call automorphic form. So modular form usually refers to a holomorphic form with respect to a congruence group. Automorphic form, in a sense, it's more general analytical object. And in doing this, Maass introduced spectral, serious Hilbert space analysis into number theory. For example, he had to know that the dimension of the he had to look at the spectrum of the Laplacian on cusp forms and know that it was a discrete sum, which he does. And this is particularly interesting even to analysts, I think, at this time, because arithmetic quotients are not compact. So you really have to be rather careful. I haven't read Maass's paper in a very long time, but his analysis is kind of primitive in a way, but it still he gets the job done. What's strangest of all, though, is his theory of Eisenstein series, because here analysis of the Eisenstein series is distinctly unsatisfactory because he has to look at the individual terms in the series expansion, which involve Whittaker functions and difficult properties of the classical zeta function. And in order to get the properties he needed, in particular a functional equation and meromorphic continuation of his Eisenstein series, it's very special to this arithmetic situation. He was unsatisfied with this, and very interestingly, he got a student of his named Rilke to try to prove analytically a Plancherel theorem for arithmetic quotients and the continuation of Eisenstein series. Rilke succeeded only partially, but the problem was finished off very famously by Selberg in a very clever trick. And eventually several tricks. Selberg came up with several different proofs of the way Eisenstein series behave, the Maass's Eisenstein series behave. Even now, it's not considered entirely trivial, although there are very slick things known. So Selberg used this in turn to arrive at his trace formula, and that led in turn to being able to calculate eigenvalues. This was done also by Eichler at the same time. So at this point, with Selberg's formula for the Eichler-Selberg formula for the trace of Hecke operators, Glashier's table has now become a graduate course exercise, which is kind of cute. It took quite a while, but it did happen eventually. So in order to understand what happened next, I have to say something about a different way of explaining what an automorphic form is. So let me tell you what, I want to explain what Maass's definition would be in modern terms. So the set of all lattice bases in C is a principal homogeneous L2R. So if I fix one, then I can define a function on the group by its transform of that fixed basis element, fixed basis. So modular forms of weight K become functions on the group quotient G modulo gamma, satisfying now the formula that I write here, where lambda is a member of the particular copy of C star embedded in GL2. It also satisfies some differential equation. If it's holomorphic, it's something related to the Cauchy-Riemann equations. If my function is a Maass form, then it's something to do with the Laplacian. In general, it's some sort of generalization of the Laplacian. So it's an eigenfunction for a certain elliptic operator on the group G itself. And it satisfies some growth condition, which again, I won't explain. So that's what Maass's idea led to eventually. We move from functions on lattices or functions on the upper half plane to functions on G quotient, the arithmetic group gamma. And so an automorphic form of level n is now a function satisfying the growth condition on G modulo gamma of n, such that first of all, it multiplies multiplicatively on the right by an element in the copy of C star in GL2R. And second of all, it's an eigenfunction for some differential operator, which happens, it's called the Casselman operator. So the Hecke operators also act on this space, and they act as self-adjoint operators, and the spaces are finite dimensional because that's what the Hilbert space analysis tells you. And so we can assume as well that F is an eigenfunction for the Hecke operators. So now for each prime P dividing N, there exists a number CP and an epsilon, character epsilon, such that my function F satisfies these properties. It's an eigenfunction with respect to TP and also with respect to TPP. And well, the subspace of Cus forms are functions which vanish with actually infinity, because that's what the series expansion tells you. So this includes both Hecke's and Maass's cases, and other cases as well, although Hecke's and Maass's cases are the best ones, the most interesting ones. For a given n, chi, and eigenvalue of the Casselman operator, the space of automorphic forms has finite dimension. Then we have an L function attached to it, which we can generalize. So we can wonder, is the function analytic? Does it satisfy a functional equation? Does it satisfy in any way a form of the Ramanujan's conjecture? And in fact, well, yes, the answer is, it's a bit complicated at this point. Around the time of Maass and so on, there was a functional equation known, but the question of what to do, so we can define it very easily when P does not divide n. When P divides n, one has to be a little more careful. And there are some really bad cases where there are extra little factors which were not understood at all at this time. But anyway, when you throw in some factors, and so Hecke and Maas were kind of vague about this, but there was some factor to throw in. Function becomes entire and satisfies a relatively simple functional equation. So the question is, let's look at this a little more carefully. So suppose that I have a Cuss form of the right type, and then I follow Ramanujan and I factor my polynomial, my characteristic polynomial of the Hecke operator. I factor it like this. So I write my denominator in the polynomial associated to the denominator in this way. I factor it as x minus the product of two roots, where the product here is equal to this. So the epsilon is a finite character, so this has absolute value 1. So the absolute value of the product is equal to this. And this determines the conjugacy class in GL2C. And so now what we have is, so I want to point out that there's no sense to choosing the order. There's no order of alpha over beta, so you get a pair, an unordered pair of alpha and beta, and that determines the conjugacy class, and that works perfectly because the conjugacy class is also only determined up to a permutation of the alpha and beta. So an automorphic form is characterized by an infinite family of conjugacy classes for P relatively prime to N. Now, we can always change F harmlessly. So I can multiply F by a determinant factor so as to arrange that the absolute value of chi is equal to 1. And with this normalization, the absolute value of the product of alpha and beta is equal to 1. And then you can wonder, Ramanujan's conjecture in his case becomes the fact that the conjugacy class is unitary. And that's the generalization of Ramanujan's conjecture to arbitrary automorphic forms in GL2 for Cuss forms. So I should mention, because it's important, but I won't mention it again, there is one modular form which is often forgotten about, and that's the constant functions, which do not obey Ramanujan's conjecture. But of course, it's not a Cuss form, so we don't have to worry about it. One of Langlands' ideas, in a way, the main idea is that the set of conjugacy classes is an extremely strong characteristic of the automorphic form. And furthermore, he conjectured that a similar construction works for arbitrary reductive groups. So it's easy enough to see that you can generalize Mordell's definition of Hecke operators to functions on GLN of Z into GLN of R. You can define a polynomial algebra of Hecke operators. This was done by Tamagawa a little bit later. And you can specify for all but a finite number of P, a conjugacy class in GLN associated to the form. I don't know who first did this, but it was maybe Jacques and Godema, really. But the beginnings of this were first done by Tamagawa, who was trying to generalize Tate's thesis. Used different terminology, but still the basic idea is there. So we get automorphic forms on any group is attached to something, some conjugacy class in a complex group. So to look at an interesting case, let's take my sigma to be the standard complex representation of GL2C, the one that occurs in Ramanujan's conjecture. And its symmetric powers are also irreducible representations. And this gives us an embedding of GL2C into higher dimensional GLNs. And so the set of GP of conjugacy classes gives rise to a set of conjugacy classes in GLN plus 7C. And basically, Langlands' functoriality conjecture is that there exists an automorphic form on GLM plus 1 corresponding to it. And in fact, to give part of the game away, this was apparently verified by classical modular forms just a few weeks ago by two English mathematicians. So one consequence in turn would be that this satisfies an entire function. This is definitely a result of Jacques and Godema, is that under these circumstances, this definitely satisfies an entire function with function equation. And yet a further consequence would be, if I knew this for all symmetric powers, it would be a verification of Ramanujan's conjecture and also the statistical distribution of the elements GP. So somehow it all comes down, so the idea of, basically Ramanujan's idea of considering the pair alpha and beta as being an invariant of the distribution form is actually an extremely fruitful one, and it's been general. It's exactly what Langlands' definitions generalize. Oddly enough, this is also related about the same time that Langlands started working on this earlier in the 60s, around 1964. Tate had looked at distributions of Frobenius's and analytic cohomology on algebraic curves and came to a similar statistical distribution. Of course, it's related to Langlands conjecture now. Okay. So there are some exceptions. The Ramanujan distribution, what I call the Ramanujan distribution, is not always valid for some automorphic forms for GL2. And one of the exceptions is one we've already seen. There's a Cuss form attached to the Q adjoining the square root of -1. We had my supplementary term chi of 4 of n, and I wrote down the formula for this. And if you look at this distribution, well, you get either 0 or a uniform distribution, as I mentioned. And well, that means something a little odd is going on. So you get each automorphic form somehow has a signature defined by that statistical distribution. This in Langlands theory, this eventually becomes something called the functional source of the modular form, which I won't be able to say something about, but it's one of the deepest questions in the Langlands theory. And in this case also, I should say that Langlands attaches a group, so he attaches a complex group to GLN over Z, he attaches the complex group GLN of C. In general, to an arbitrary algebraic group, he attaches a dual group. The dual group often, in general, has a Galois component, and that's what happens here. In this case, we're looking at an algebraic torus determined by the algebraic extension, K over Q, and its L group is actually has a Galois component. It's a group of two different connected components, this and this is the quotient. Somehow that's connected with, well, that's his L group with a Galois component. There's a more famous example. So one way we're interested in getting conjugate classes, well, we're interested in getting elements of GL2C, which are in some way associated to finite primes. And one way of doing that is through Artin-Galois representations into GL2C. So Artin is defined for these in L function. And Langlands proposed that in fact, if Artin's functional equation holds, then this has to come from an automorphic form of some kind on GL2C. This is verified in all different kinds of examples, but it's still a very, very difficult open question for Galois extensions of Q, which are not, with two-dimensional representations, which are not solvable. It's a kind of non-abelian reciprocity theory. And it partially justifies my statement earlier. It's clear that in order to understand number theory completely, modular forms and automorphic forms are really an essential component. So here I can say something about arbitrary groups. So for groups G other than GLN, there are unavoidable technical difficulties, but to every one of these, Langlands associates an L group, which, as I say, for GLN is just GLNC, but in general, it's rather more complicated. It's what's called a dual group, which is to say that its root system is a dual of the original root system. The dual of the symplectic group, for example, is SO odd. And so, well, we always get a family of conjugate classes. We can define L functions. And Langlands' implicit conjecture is that the right L functions are always automorphic L functions defined in his sense, that other L functions don't really play an important role. That the proper study of L functions should be restricted to automorphic L functions, including Galois components. And a homomorphism, the functoriality conjecture is that a homomorphism of L groups corresponds to an embedding of functional equations is by considering all of these. So now the techniques are limited. So far we've looked only at Z and Q, but Z is a principal ideal domain. If you look at other fields, you get into deep trouble immediately arising from class number problems. So you have to generalize Mordell's theory, not just, you don't work with arbitrary global Hecke forms, but you have to somehow transform things to p-adic groups where life becomes much simpler in a way. And that's Langlands' proposal also. So in order to do that, you have to move your arithmetic quotients to become Adel arithmetic quotients. And there are complications which occur in the original Langlands proposal. He discovered a phenomenon called endoscopy eventually, which said that automorphic forms are not actually characterized by the set GP, but only up to finite ambiguity. Now people have won prizes for this. So there's unfinished business. Well, as I say, Ramanujan's conjecture on the size of P is related to functoriality in a strong sense, and that's been verified. And in fact, Ramanujan's conjecture has been verified strongly and for different reasons, different versions of Ramanujan's conjecture by these English guys recently. It's not at all apparent. So the main conjecture of Langlands is functoriality, and it's not at all easy to even predict what will happen or when it will be verified. There are very few people working on it directly at the moment. Jim Arthur is one of the few I know. But it's not clear at all what's happening. Langlands has made some proposals around the year 2000 that tried to configure. What you want to do is, according to Langlands' idea, which may or may not be true, but I think it's likely, is that the basic tool you have is the Selberg trace formula as generalized by Arthur. And there are many results that it's produced, but there's somehow there has to be some major rewriting of the trace formula in order to prove Langlands conjectures. People are working on this, a few people, but not very many. And it's a very hard analysis of an arithmetic nature. It's not easy to predict what the future will involve. There's one extra thing I'd like to talk about. At the beginning, we talked about sums of squares, and then later on, we talked about Hecke's generalization to other quadratic forms. The question is, what does Langlands' conjectures of functoriality say about how theta functions in quadratic forms give rise to automorphic forms? What's known is largely due to Stephen Rallis, who applied results of Eichler and Siegel and Andre Vey. But I have to say that something, I looked over this work recently for this talk, and it's kind of, I would say unsatisfactory, but that may not be a fair statement. It doesn't quite, Rallis's work doesn't quite fit in with Langlands' conjectures. There's no simple map of L groups which gives rise to theta functions. Okay, I'm through. Are there any questions? Hello?
Are there any questions? Doesn't seem so.
Okay, I'm through.
All right, well, thank you for the talk.
Okay.
Thanks, Bill.
Yes.
Nice talk.
Oh, okay, thank you. It was fun making it, actually. Thanks for the invitation. Although I have to say, the original invitation was to go to Beijing, which means I eat better.
Well, you could still come if you want to.
Here I am struggling to get breakfast, but anyway, no, I'm not going to travel to Beijing in the near future.
Good food here.
Yeah, okay, thank you.
It looks like we have a question in the audience. Can you give a moment?
We have to translate the question.
Here, I'll allow this person to talk.
We have many questions, no? Yes.
Marianne, I think I gave you permission to speak. You have to unmute yourself.
Oh, greatest common divisor. So there's one question I can answer. Somebody asked, what does MN mean? I mean by this the greatest common divisor. Yes, the slides are available online, as I said in the talk. Yeah, I can't find. Yeah, the slide, yes.
We can post a copy of those slides on our website with your permission.
Yes, so I presume Harvard is going to post the slides, but the slides are also available at UBC. And yes, and here's the address there. Okay, any other questions? No?
There's one person where I'm trying to unmute, but I think she may be having technical difficulties. So.
Yeah, I think we have trouble unmute her.
We have trouble with what?
Marion, can you put your question into the Q&A chat? Just can you type it out? I think that may be easier.
Yeah, no, there's no questions. Okay. No, I think I'm through.
Oh, she just put something into the chat box if you want to read that.
Oh, I don't see it. No. No. No, I think I'm done.
We have questions both in the Q&A and in the chat.
Oh, we get another one. Ah, yes. I don't see it.
Oh, is
Can
there
you
a
read those out,
reference
Ying?
to the recent proof of Langlands functoriality conjecture by the two British mathematicians?
I'm sorry, say it again very slowly.
Is there a reference to the recent proof of Langlands functoriality conjecture by the two British mathematicians?
Yes, yes. Right there. So it's by Jack Thorne and James Newton. And I think their work is probably related to earlier papers by Barnett, Lamb, Garati, Harris, and Taylor. This is the second paper in a series. They're all interested in, so this is a totally different direction in automorphic forms from that imagined by Langlands, but probably certainly inspired by Langlands' original conjectures. There's a notion of p-adic automorphic form, which has become extremely interesting in recent years. Whereas all of Langlands' work just relates to complex representations, but the p-adic theory has become extremely valuable, and that's what these guys are doing. It has limitations in a sense. It only applies to holomorphic, or forms which are in some sense related to cohomology and holomorphic functions. Anyway, that's certainly the reference. You can see the reference, right? Yep, I'm sharing my screen. Any other questions?
Yeah. Another question is, dual groups occur in quantum field theory, magnetic monopoles. Any comments?
The answer is, I do not know. I know nothing about quantum field theory. I think the answer is yes, but I really don't know. In a different way, what distinguishes Langlands dual groups is that they have a Galois group component, which is often neglected by people working on dual groups, but in Langlands theory, it's extremely crucial. Otherwise, the functoriality conjecture makes no sense. And with the Galois component, the functoriality conjecture becomes extremely interesting because it includes as well the Artin conjectures. What was special about Langlands' original invention of the L group was that it included the Galois component right from the very beginning, almost from day one, I would say. And there's actually one real theorem in his letter to Weil, which became very famous, which relates the conjugacy classes in arbitrary L groups in a highly non-trivial fashion, which took quite a long time for people to understand.
Any other questions?
I need somebody to read the questions. I do not see, no. Okay.
I think that may be it.
Okay.
That we have.
Okay, so thank you very much for the talk.
Okay.
And it's a shame that you aren't able to deliver it in person, but this, of course, is much better than nothing. So thank you again.
Okay, thank you, Bill.
Okay, bye-bye, Shington.
Bye-bye.